In this video, we're going to look at stationary points, local maximum, local minimum, and point of inflection. So the first example we'll look at is find the coordinates of the stationary point of the following function. 2x squared minus 6x plus 1. So we'll just take a look at the first example, which is a quadratic equation, and we're given the function was y equals 2x squared minus 6x plus 1. Now to find the turning point, we get the first derivative, dy dx, which gives me the slope of the 4x minus 6. It's the slope of the tangent. Now the tangent at a stationary point always equals 0. The slope will equal to 0. So in this equation, dy dx is 4x minus 6. Set it to 0 and solve for x. So x will be positive 6 over 4 or 3 over 2. Now we're asked to find the coordinates. So I'll pop the 3 over 2 into the equation and we will find the y value. So we're going to have 3 over 2 squared. No, we're going to have 2 times 3 over 2 squared. 2 times 3 over 2 all squared minus 6 times 3 over 2. Back on that one, I wasn't watching what I was doing. 2 times 3 over 2 squared minus 6 on 3 over 2 plus 1. So we get the y value of minus 7 over 2. So the coordinates we have in this case will be y equals minus 7 over 2. So the coordinates of the turning point, 3 over 2 minus 7 over 2. And we determine now, we know this is a quadratic equation where 3 over 2 minus 7 over 2 could be something like this. We can see it is a minimum, but let's just show by finding the second derivative. So d2y dx squared is equal to 4. 4 is greater than 0, therefore we have a local minimum. Okay, so that's the first example, a simple quadratic equation, and we'll just move on now to look at the next example. So example 2, find the coordinates of turning points for the following function. And we're given a cubic equation, x cubed minus 3x squared minus 9x plus 11. And determine the nature of the turning points and show there is a point of inflection when x equals 1. Okay, so let's just note the cubic equation we have was, and we have y equals x cubed minus 3x squared minus 9x plus 11. So the first thing is to find the coordinates of the turning points. First derivative, set it to 0. dy dx is 3x squared minus 6x minus 9. We'll set that to 0 because we know that's where the turning points occur. I'll factor out the 3. Minus 2x minus 3 equals 0. So we can factor this. We have a 3, we have an x minus 3 and an x plus 1. So that will give us two x values of x equals positive 3 or x equals minus 1. So when we sub in to find the y value, we'll sub in the x equals 3 into the cubic. So we'll have 3 cubed minus 3 times 3 squared minus 9 times 3 plus 11, and that works out to be negative 16. You can check that yourself on a calculator. Ry equals same, sub in the 1, you get a positive 16. So the coordinates we're looking at are 3 minus 16, and the second one is minus 1 positive 16. We're going to determine the nature of those by finding the second derivative. So d2y dx squared equals 6x minus 6 when x equals 3. We're going to have 18 minus 6. The second derivative d2y dx squared is positive 12. This is greater than 0, so we can say it's a local minimum. And when x equals negative 1, the second derivative equals negative 12. This is less than 0, so we can say we have a local maximum. And finally, to show there is a point of inflection, so when x equals 1, the second derivative is 1 minus 6 equals 0. So we can say point of inflection when x is 1. Okay, so that's the second example. Let's move on to the final example. So find the coordinates of the turning points of the following function. We have 2x cubed minus 9x squared plus 12x plus 1. Determine the nature of the turning points and hence sketch the curve. So we'll take a look at this one. The cubic we're given was 2x cubed minus 9x squared plus 12x plus 1. So that's our function y. The first derivative, dy dx, equals 6x squared minus 18x plus 12. Set that to 0 and solve for x. So I'll factor out the 6. So we've got 6 on x squared minus 3x plus 2 equals 0. And we'll further factor it to get two values for x. So we have minus 1 x minus 2 equals 0. So the x values we're interested in, x could be equal to positive 1 or x equals positive 2. So when so we'll sub in into y and we get y equals. Now I've done this earlier, so this will give us a value of y equals 6. We sub 1 in, and if we sub 2 in, y equals 5. So the coordinates of the turning points will be 6, oh, not 6, it's going to be 1, 6, 1, 6, and the second turning point is 2, 5. And we need to determine which is the maximum, which is the minimum. So second derivative, d2y dx squared equals 12x minus, no, minus 18. So when x equals 1, the second derivative, d2y dx squared equals minus 6. This is less than 0, so we have the point 1, 6 is local max. And let's just sub in x equals 3. We get the second derivative. Subbing in 3, we've 24 minus 18 is positive 6. And that we know is greater than 0, so we have a local min. Now this will help us sketch the curve. We know the turning points, so let's just draw a curve. I'll go back up to have a look at the critical values. We've got a y-intercept there. We have 1, 6, and we have 1, 6 is local maximum and 2, 5. So we could call that 1, call that 2. So we've got a curve that's going up and it's turning at 1, 6, and it is turning again. That's not a great, I'll do that again. Okay, so we've got a curve that's going up, turning at 1, 6 and turning again at 2, 5. That looks better. So I'll just finish the sketch by going y and going x. And we need to mark 1, 2. We need to show the y-intercept is 1, positive 1. And we could mark this as 1, 6. And we could mark this as 2, 5. So that's everything completed now for this example. So thank you for watching, and we'll just stop the video now.